Hi everyone. Today I'd like to talk about freefall. And our goal here is going to be to use the kinematic equations we learned to solve problems for objects moving at a constant acceleration while they're in freefall. Well, what is freefall? Well, first thing, freefall is an object that is not being acted upon by any force other than gravity. So for example, while I'm holding this pen, it's not in freefall. If I let go, while it's in midair, the only force acting on it is gravity. Well, wait, you might say, what about air resistance? You're absolutely right. In reality, air resistance is also acting on this pen when I let go of it. However, for the purposes of this course, we're going to neglect air resistance. So free fall is a situation where we do not have air resistance or air friction acting. For example, if we drop this ball and sheet of paper, it's pretty obvious that the ball is going to fall faster than the paper. However, if we could remove the air from the room, we would find that they fall at the same rate. And Commander David Scott actually did this on an Apollo mission. When he was on the moon, he dropped a hammer and a feather at the same time, and they both fell at the same rate. They hit the ground at the same time. So we're going to analyze the motion of objects while they're falling or being thrown up, while the only force acting on them is gravity, and we'll neglect air resistance or air friction for the purposes of this course. Later on in other physics courses, you will go into considerably more depth on air resistance. Now, the acceleration due to gravity is how much an object near the surface of the Earth accelerates toward the center of the Earth. We typically think of this as a constant at 9.8 meters per second squared. But in reality, this acceleration due to gravity, this constant that we give the symbol lowercase g, is a bit of a misnomer. Really, what we should call it is the gravitational field strength near the surface of the Earth. And it is that as well. But what it's really trying to tell you is if we drop this ball, it will accelerate toward the center of the Earth at 9.8 meters per second squared. It'll accelerate 9.8 meters per second every second. As we move further away from the Earth, g decreases, and as we get closer to the center of the Earth, or if we were on another planet that's more massive, and we'll learn more about gravity later on, but g can actually change on other planets. So, near the surface of the Earth, the acceleration due to gravity, the acceleration experienced by an object in free fall, is 9.8 meters per second squared, always toward the center of the Earth. Now we'll start off by talking about objects that are falling from rest. Anything that we drop or that falls from rest has an initial velocity of v0 of 0. Now when we talked about the kinematic equations, we said we're going to call the direction of an object's initial motion positive. So for an object dropped from rest, since it's initially moving downwards, we'll call that the positive direction. Then when we look at the problem, we also realize that the acceleration, which is down toward the center of the Earth, points in the same direction as our positive axis. Since they point in the same direction, our acceleration is going to be positive g, or positive 9.81 meters per second squared. Other than that, it's just a standard kinematics problem. Let's take a look at an example. How far will a brick starting from rest fall freely in 3 seconds? Neglect air resistance. Well, we can figure this out by first recognizing that this is a vertical motion problem. Since the object will go down first, we'll call that the positive direction, down, and we'll set up our vertical motion table, v0, v, delta y, a, and t. And since it starts from rest, v0 is equal to 0. Delta y is what we're trying to find, and we know the acceleration is positive g. Positive because acceleration points down and positive is down. So that's going to be 9.8 meters per second squared. We don't know what our final velocity is. We do know that time is 3 seconds. So, trying to find how far it falls, that's delta y, we need to pick a kinematic equation that has most or all of our variables in it. Well, the one that comes to mind very easily is delta y equals v0 t plus 1/2 at squared. And a nice trick for simplification, if you notice that v naught is 0, 0 times anything is 0, so that whole term becomes 0. This simplifies to delta y equals 1/2 at squared. Now we can substitute in our values with units to say that delta y equals 1/2 times our acceleration, 9.8 meters per second squared, times the square of our time, 3 seconds squared. And when I do all this, plug it into my calculator, I should come up with a delta y, or a vertical displacement, of about 44 meters. And notice our answer is positive. That means that it was displaced in the same direction that we called positive there. So it was displaced 44 meters down. Of course that makes sense. You wouldn't drop a brick and have it fall upwards. Let's take a look at another problem. This time we have a ball that's thrown straight downward with the speed of 0.5 meters per second from a height of 4 meters. What is the speed of the ball 0.7 seconds after it is released? Well, we recognize right away it's a vertical motion problem, and the initial velocity, the initial motion of the ball, is going to be down. So let's call that our positive y. Now we can make our vertical motion table. V naught, V, delta y, a, and t. We know the initial velocity is 0.5 meters per second down. Since it's down and we call down the positive direction, V naught is going to be positive 0.5 meters per second. We're trying to find the final speed, so there's our find. Delta y. Ooh, this is tricky. It says it's thrown from a height of 4 meters. But it doesn't ask us delta y, and it doesn't say the total distance traveled by the ball in this time is 4 meters. So we really don't know delta y. Got to read that one very carefully. Acceleration, well, acceleration points down, and positive y points down. They're in the same direction. Therefore, this must be our positive g, or 9.8 meters per second squared. And we want to know the speed after 0.7 seconds has elapsed, so t is 0.7 seconds. Now we can go and we can solve for our final velocity directly. We know v naught, v, a, and t. We have a kinematic equation with those variables in it already. So we can say that v equals v naught plus at, or v equals 0.5 meters per second plus 9.8 meters per second squared times our time, 0.7 seconds. Handy dandy calculator should tell me this is about 7.4 meters per second.